Hey there, welcome to the video discussing Chapter 2, Part 3. Sorry I can't be in class today. I'm home taking care of sick family members, but you should still be able to get all the information you need from these notes. So we're going to talk about the fundamental theorem of algebra, linear factorization theorem, and complex conjugate zeros theorem. So this is basically an extension of our previous notes on Part 2 of Chapter 2. So first off, what is the fundamental theorem of algebra? Basically, it states that a polynomial function of degree n will have n complex zeros. And complex zeros are all the zeros you can think of, both real and imaginary. And some might be repeated. So we would state to have a multiplicity of like 2, 3, 4, or whatever. So if you have a degree 6 function, you'd have 6 zeros, including real and not real. The factor theorem extends to the complex zeros of a polynomial function. So if k is a complex zero of a polynomial, if and only if x minus k. So like, for example, if you have like 1 is a complex zero, then x minus 1 would be a factor. Or if you have an imaginary number, say like 2 plus I, then x minus parentheses 2 plus I would be a factor of your polynomial. So this gives us more range with how we could look at a function, not just real zeros, but also imaginary zeros. And if we combine this with the fundamental theorem of algebra, then our linear factorization theorem states that as long as our polynomial has a degree that's n bigger than 0, then have precisely n linear factors like this. F of x equals a, which is your leading coefficient, x minus z1, z1 is the first zero, x minus z2, z2 is the second zero, x minus z3, z3 is the third zero, and so forth. All until you get to the last one, which we'll call the nth zero, zn. And of course, these could be repeated too, right? Because what if like x equals 1 shows up, has a multiplicity of 2, right? Then you write x minus 1, x minus 1. And again, they might be repeated. And z sub I are not necessarily distinct numbers. So there you go. So let's do some examples. For this first example, multiply out the factors of the function, write it in standard form, identify the zeros of the function, and the x-intercepts as ordered pairs. So this is basically just foiling. That's all you're doing here. Oh, hold on a sec. Just bought myself a new stylus. I'm not sure if it's working. Here we go. Oh, goodness. What is happening here? Why is it not working? Hold on, guys. Sorry. Can't just use my mouse. Sorry about that. So yeah, we're gonna FOIL. So so you have excuse me, x minus 5. And then this right here, that's gonna be x squared minus xi root 2 plus xi root 2 minus I squared times 2. And those cancel after you FOIL. So you have x minus 5, x plus 2, sorry, x squared plus 2. Continue FOILing, and you should wind up with x cubed minus 5x squared plus 2x minus 10. And the zeros, I mean, that's pretty obvious. There are 5 and plus or minus I root 2. They only have one x-intercept, though, which is 5 comma 0. So the graph will look probably something like this, is my guess. But you're still going to have 2 other zeros. You just can't see them because they're imaginary. Move on to part B. We FOIL again. I'm going to try to style this one more time. Just spent 20 bucks on it and don't know why it's not working. That is frustrating. Okay, we'll split it away. So you have x squared minus 9, and that's going to be x squared plus 1. Keep going, it's x4 minus 8x squared minus 9. X-intercepts are plus minus 3. Sorry, those are your zeros. But x-intercepts are 3 comma 0 and negative 3 comma 0. Let me write that more neatly. Sorry about that. But the zeros are plus minus 3 and plus minus I. Again, 3 comma 0 and negative 3 comma 0. Okay, moving right along. The complex conjugate zeros theorem. So if you have an imaginary zero, and as long as all the coefficients are real, then the imaginary zeros have to come in pairs. So the complex conjugate will also be a zero, or a minus bi. Again, this only applies if all the coefficients are real. So if you're asked to write upon a function of minimum degree, so you don't want to make it too big, with real coefficients, you can do x plus 3, x minus 4, and you do x minus parentheses 2 minus I, and x minus parentheses 2 plus I. At that point, you're technically done. And again, the leading coefficient, we'll just make it 1. But if you were to put this in standard form, actually, we're not technically done because it did say standard form. Then you have to FOIL. I'll FOIL the first two. That's pretty easy. X squared minus x minus 12. Now for the next one, you can get a little creative here. What I suggest that you do is do a little swap here. X minus 2 plus I, x minus 2 minus I. Then you do this. X squared x minus 2 squared minus I squared. And I'll let you guys take a moment to work it out. You should get x squared minus 4x plus 5. You do all correctly. And then final answer, just take a moment, you can pause the video and work it out. You get this. Okay, but it's kind of tedious to go through the whole process. So just gave you guys the answer. For example 3, more of the same stuff. You're going to do x minus 1, then bracket x minus 1 plus 2i, bracket x minus 1 minus 2i, and then need some space here, x minus parentheses 1 minus I, and bracket x minus 1 plus I. Now, one way we could do this, if it helps, and I'm not going to make you guys FOIL the whole thing, so we could just leave it in factored form with real coefficients still. But one thing you could do as a shortcut is think about how this would look at if you're given the equation and how it would look as the end result. The end result would look like this, right? If you had an equation here and went through the process of factoring and solving, ultimately you get x equals 1 plus minus 2i, x equals 1 plus minus I, and of course x equals 1. So what I'm going to do is this, kind of a creative way of doing this problem. X equals 1 plus or minus 2i, x minus 1 equals plus minus 2i, and then square both sides. You get x squared minus 2x plus 1 equals negative 4, because remember it's I squared. So that's a factor it comes from. Do it again. And of course, you also have x minus 1. So the answer would look like this. And there you go. It'll keep on moving. Example four, oh boy, this is crazy, crazy long. Well, anyway, you're asked to find all the zeros of this and then write in its linear factorization. So one thing we could do is start with synthetic division and also figure out all the possible rational zeros. So remember the p's over q's, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, all over plus or minus 1. Now, yeah, I'll let you use a calculator to find one of the zeros because that'd just be kind of crazy to do this by trial and error. Negative 2 will be one of the zeros. So if you were to graph this in Desmos or a graphic calculator, you'd find negative 2 would be one of the x-intercepts. And write all the coefficients here. And if you want to use long division, you can, but I think synthetic's actually cleaner. And remember, any term that gets skipped over, you got to put 0 as a placeholder. Bring down the 1, multiply, add, multiply, add. Just be really careful, multiply, add, multiply, add, multiply, add. So this now becomes x to the 4 power minus 5x cubed plus 5x squared minus 5x plus 4. Okay. Then we'll do it again. And if you were to switch colors for a bit of contrast, if you do also investigate the original function, what other x-intercept you got, you'd have 1 as well. So 1 will definitely work for the remaining polynomial, right? Just because it should. 1, 1, negative 4, negative 4, 1, 1, negative 4, negative 4. Sorry for the messy handwriting. These are 5s. 0. So it's x cubed minus 4x squared plus x minus 4. Now, if you factor, you factor by grouping. And now we got everything, right? So we'll do this in blue. So it's x squared plus 1 as a factor, x plus 2, x minus 1, and x squared plus 1. But if you wanted to write as linear factors, x squared plus 1 needs to break down even further. Go write as x plus I, x minus I. That would work. What else? Yeah, just to write the linear factorization, all the zeros are plus minus I, negative 2, 1, and 4. Okay, so that's example 4. And then let's take a look at example 5. You're told that that's one of the complex zeros. Find all the other ones. So you could actually do synthetic division with 1 minus 2i. It takes, it's going to be a little careful here. So 4, no x cubed put 0, 17, 14, 65, 1 minus 2i. And I did not leave myself enough space. So let me space this out a bit better. Four minus 8i, 4 minus 8i. One, that's not going to be fun, but you do get negative 12 minus 16i. I have the answer key in front of me, so I'm kind of cheating. And 5 minus 16i. Do it again. I should get negative 27 minus 26i, which would be negative 13 minus 26i. Do it again. You get negative 65, and you get 0. But then 1 plus 2 I should also work too. So 4. 4 plus 8i, that's 0. Oh, sorry, it's 8. Then 8 plus 16i. Ooh, this comes out very nice. 13. Ooh, look at this. 13 plus 26i. And you get 0. And then this is just a quadratic. You could probably use quad form at this point or complete the square, whatever you prefer. If we quad form this, I trust you guys can do just fine, but I'll just tell you what the answer is. It's going to be -8 plus or minus 12i over 8, or -1 plus or minus 3 halves I. And then if we're asked about the linear factorization of it, it's kind of long, but we'll do it. It's going to be x minus, so I'll put another parentheses, -1 minus 2i, x minus 1 plus 2i, x minus -1 plus 3 halves I, and x minus -1 minus 3 halves I. Okay, down to the last page. So you've noticed every time we FOILed out two linear factors, each contain one of a pair of non-real complex numbers, always resolve a quadratic polynomial, blah, blah, blah. So anyway, every polynomial function with real coefficients can be written as a product of linear factors and irreducible, meaning you can't simplify irreducible quadratic factors with real coefficients. Now the irreducible quadratics will have no real zeros. So that's what we just saw in the previous example. And actually, if I go to the filled out notes, sorry. Yeah, we had 4x squared plus 8x plus 13. There you go. Problem function of odd degree with real coefficient will have at least one real zero. It's got to cross at least once because the other zeros could be imaginary, but they come in pairs. So you expect at least one real zero with an odd degree. Even degree, like if you have degree 4, your curve could look like that, right? I mean, it's actually, sorry, it should be more smooth than that, like a W. But odd degree is going to cross the x-axis at least once, and that's because, you could have something kind of like this, or you have something kind of like this, right? So that's what's happening there. So here we're going to algebraically determine all the zeros. Remember, as a product of linear and irreducible quadratic factors, each with real coefficients. So we do the P over Q business. We're still use a calculator anyway, but at least, we'll know what to expect. Plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. All over plus minus 1, plus minus 3. But we'll if we use a calculator, you'll find it 2/3 one of the zeros. 3, -2, 6, -4, -24, and 16. So you have 3, 2, 0, 0, 6, 4. Oh, it comes out really nice. Look at this. -24, -16. So now we got ourselves 3x to the 4 power plus 6x squared minus 24 equals 0. You can actually factor out 3 from that. And then think of it like a quadratic, right? Think of it like, oh, -8, my bad. And I'm actually glad I caught that because I still would have been able to factor that one. Or would I? -12? No, I wouldn't have. So you have, excuse me, you're gonna have x minus 2/3. You have 3 on the outside. X minus 2/3. You could write as 3x minus 2, but I would pull the 3 out. And you have x squared minus 2 and x squared plus 4. But x squared minus 2 can be broken down even further. X minus 2/3, x minus √2, x plus √2. So those are your rational, or what do you call it? The conjugates, but radical conjugates, I guess we don't call it that. And x squared plus 4, we can't do anything about that. That's not reducible. That's if you want to keep everything all real, if you don't want to use imaginary. I mean, yes, you can write as x minus 2ix plus 2, I suppose, but if you want to write with just real coefficients, as I said here, as an irreducible quadratic, then that's what you do. And the zeros, of course, are 2/3 plus or minus root 2 and plus or minus 2i. Okay, that should conclude the notes. You'll then start the homework. Homework will be, and I didn't do a review of the homework, but this is the homework that we had last week. There's homework 4 handout, and the solutions are here if you need to check your work. But the homework that I'll have you guys work on will now be homework 5. And you can see using rational zeros to find zeros. Kind of the same stuff we just did. Just kind of a lot of rinse and repeat. There's one IVT problem, so that's good review as well. And the answer key should be up in Schoology as well. So I'll make sure you have everything you need, and in Schoology, and that's all. Okay, be well, and I'll see you guys soon.